should be loading in a few seconds.
I guess we are live.
Oh, awesome.
Okay, let's take it away.
Should we go?
Yeah, let's start the call.
Perfect.
Cool. So welcome to first ever episode of Stackit. Today is going to be an amazing day because you've joined the first episode of Stackit, and this is the next big thing after merge. Okay, that was too much, but yeah, it is a special day, and if it's not, we'll make it special for you. Now, you will say, or you must be saying, what is this Stackit, right? So Stackit is going to be a series where we bring in some amazing folks from the world of Web3 and have casual, fun, informal, unscripted discussions with them. So don't think it to be all serious. It will be serious and fun, just like the merge. Okay, brother, stop it with the merge jokes. Now, this other question that you may have, like, what is this Chainstack logo you've seen everywhere, like in the post? It's been making a lot of name recently. So Chainstack is the company that employs me. Jokes apart, Chainstack is the leading suite of services that connects developers with Web3 infrastructure, powering applications in DeFi, NFT, gaming, analytics, and everything in between. So if you are a startup or large enterprise or anything in between, Chainstack enables thousands of companies to cut down the time to market, costs, and risk associated with creating and scaling decentralized applications. We do this by offering fast, reliable, and easy to use infrastructure solutions distributed globally. We make sure innovators like you can focus on what's important. So go check out chainstack.com, super cool company which employs me. Lastly, you must be thinking, why is Mrudul so loud? Because Mrudul is loud. And you can expect a couple of bad jokes here and there, so you must have just guessed it. There's no other camera at this side. Just doing this because I saw Kevin Spacey do it in House of Cards. Just wanted to do it sometime. Yeah. Without further ado, let me introduce our guest here, Matt Krak. Matthew, welcome to Stackit.
Awesome. Thanks so much for having me here. Looking forward to talking more about ZK.
Great. So to give you a background of Matt currently supports Polygon ecosystem as a developer relations engineer for Chainstack. Prior to Chainstack, he focused on driving Web3 education through Spawn Student Fellowship. He also has worked as head of business development for blockchain at San Diego, UC San Diego's blockchain club. Welcome, Matt. Great to have you here. And we're looking forward to hear a lot from you as well. And today's special guest, welcome Harsh Bajpai.
Hey, hi everyone. Yeah.
Hi.
Yeah.
There's no live audience, so I'll be doing yes now.
Yeah, sure.
So to give you a little bit about Harsh, Harsh works at Polygon ID, which is trying to bring an SSI system powered by zero knowledge. He loves working on new ideas and is also devoted towards education around ZK. Welcome, Harsh. Welcome. How are you feeling today?
Yeah, I'm feeling good and like really impressed by your super high energy, given it's a weekend and we live in the same time zone. So
Yeah. So that is something that I've realized that Web3 energy is high, but not on YouTube or Spaces. So why not bring some energy?
Why not?
Right?
Sure.
Love that.
Yeah. So so this is how we are going to move forward. We are done with the introductions. Check. I'll now let Harsh take over and walk us through ZK-SNARKs, and at last, Matt and I will ask a couple of questions to you. guys, everyone who has joined, you can just drop your comments in the chat as well. If we find something interesting, we'll ask those questions to Harsh as well. So over to you, Harsh.
Got it. Thank you. So let me share my screen. And is my screen visible?
Yes, yes.
Perfect.
Yep. Cool. Hey, hi everyone. So as Mrudul said, my name is Harsh, and today we are going to take a look at ZK-SNARKs because recently, this word ZK has been popping up a lot, and suddenly it's no more an academic term, right? Like people now the generic Web3 audience is taking interest in it, and then my goal was that how can we simplify the material around ZK, because to be honest, not everyone needs to understand the complex math behind it. And I don't think that walking someone through polynomials is the best way to introduce ZK to them. It's good for academics, mathematicians, maybe for some developers as well. But for a generic audience, this presentation is my effort to basically make at least you believe that something like ZK-SNARKs is possible, right? That is what we are going to try to do, because people understand what they are about, but they actually find it hard to believe that something like this can be true. So that is what we will try to do. We'll try to make you more and more sure that this thing, we will try to give you this intuitive feeling from inside that this thing is possible, right? So yeah, let's get started. Yeah, I'll skip that part because it has already been done. And yeah, everyone is hearing about ZK. Everyone wants to get it. And at the same time, everyone is confused, and it's a huge, problem right now. So the agenda for this particular presentation will be that we will talk about ZK cryptography, what it is in general, then about ZK-SNARKs. Then we will slightly go for a developer-focused stuff for 5 to 10 minutes. But if you're not a developer, you can still sit back, enjoy it, because it's not going to be some very complex stuff. And then we will go and look at a few use cases of ZK, and then we will wrap it up. So the first question, what is ZK cryptography? Well, a way to prove knowledge of information without actually revealing it. And before we think more about this, this line in itself is very small, and it's a simple statement. It's a way to prove that you have knowledge of information without actually revealing it. And how I would like to start this is that let's firstly look at what an ZK interaction would look like, right? So in every ZK interaction, you have two parties. One is a prover, the second one is the verifier. Prover possesses knowledge of information. Verifier desires the prover to know the particular piece of information, right? And in a general case scenario where you would what would generally happen is that prover does not want to reveal the information, while the verifier only cares whether the prover knows the information or not, and does not care what it exactly is, right? So the way a ZK interaction would work is that they would be a prover. They would have knowledge of information. They can generate a piece of data that they can call as a ZK proof. And the verifier somehow has this magical capability to verify these proof of knowledges, right? Cool. Now we just talked some random stuff, and the thing is, how is that even possible? Because this is something that anyone can even say that. No, everyone can say that, yeah, this is how ZK works. I can create any random thing and say, yeah, this is how it will work, right? So the question is that how is something this bizarre even possible, right? And the way we will look at it is that firstly, let's take a small detour, and let's not talk about proof of knowledge of information. Let's talk about something else. Let's talk about computation. And let's think what computation is, right? You have inputs, you do some sort of processing on them, you get an output, and you can summarize that as computation. Well, yeah, this is what computation is, right? Inputs, processing of inputs, outputs. So when we talk about, let's say, multiplication of two numbers, you have two inputs, X and Y, you multiply them, X and Y, that is the processing, and then you have output Z. And the question is, how do we verify computation? Well, we can recompute, we can always recompute. So basically the prover here in this case, who wants to prove that they did a computation correctly, will give the inputs to the verifier. They will give what computation they did. They will give what the outputs were. The verifier can take the inputs, do the computation, and verify whether they get the same outputs or not. So they can recompute. So hence redo the computation and verification is done. Now the question is, what about very heavy computations? What about computation that takes a lot of processing time, right? Like, is this the ideal way we would go, right? Like it makes no sense that you just recompute, right? So what can we do here? And well, what if you could prove correct execution of a computation without recomputing it? And this might again sound bizarre, but there is a term for this known as verifiable computation. So what happens in verifiable computation is that along with an output, there is another piece of data produced. It is known as proof of computation, right? So this piece of data can be used to verify computation. So unlike traditional computation, verifiable computation, you have inputs, you have some sort of a computation, you produce an output, plus you can also produce a proof of computation. So you can give someone your inputs, you can give someone your proof of computation, you can give someone your output, and they can verify your computation, right? So the question is that whatever we have talked till this far, how is this even related to proof of knowledge, right? Because we just talked about something very random. And how does it even relate with the topic that we started with? Now, what if we could hide some inputs here? This is where this gets really interesting. So in the old approach for verifying computation, what we needed was inputs, proof of computation, output, tada, you can verify computation. What I'm talking about, let's talk about a new approach where just the proof of computation and the output is enough to verify computation, right? Now, what would happen in this approach is that you can hide the inputs. So let's take a look at this circuit, right? This computation, Z is equal to X into Y. So you produce output Z, you do proof of computation, you have X and Y, which are your inputs, right? And now when you let someone verify your computation, right? What are you making them verify? You're making them verify that you know two numbers, which when multiplied results into Z, because they can verify that the output of a computation was Z. You are providing a proof of computation, means that you did the computation correctly. So the only way this can happen is that if you knew two numbers X and Y, which when multiplied resulted in Z. So for example, let's look at let's look at like like 12. It could have like factors 4 and 3, 6 and 2. Now no one would know which out of these factors you actually knew. So you are forcing someone to do certain computations. You are telling them to give a proof of that computation. You're taking, let's say, some output, and the only way they could have done that computation was if they had the inputs that you wanted. So they are able to prove the knowledge of information without actually revealing it, just by doing some computation, right? So hence proof of computation plus hidden inputs for proof results in proof of knowledge of inputs. So now let's talk about ZK-SNARKs. The next buzzwords. So what are ZK-SNARKs? Well, they're a way to implement zero knowledge cryptography. All of the fancy stuff we have been talking about till this far. It's one way to do that. And there are multiple other ways. There are ZK-SNARKs, bulletproofs, and a lot of other things. But we'll be focusing on SNARKs because I find tooling around it very good. Plus, yeah, they're good. Nothing much bad with that. And the whole comparison we can do it later on somewhere else. So, but yeah, overall, the thing about ZK-SNARKs is that the way you express computation in ZK-SNARKs is through circuits. So if someone has studied digital electronics, you have an AND gate, you have an OR gate. So you can think, so that is how you express computation. So a gate can take, let's say, inputs and it can produce an output. You can combine them together to create computation. So for example, here, if you look at it, you have an addition gate, you have a multiplication gate, and you have again another multiplication gate. So when you give it some inputs, it is doing this computation. But in ZK-SNARKs, the interesting thing is that every computation, when done, apart from the output, also produces a proof of computation. So this is what is special about ZK-SNARKs. So you can combine these primitive circuits, gates together to create any kind of complex computation you want. So you can create a hasher. So for example, you could provide it an input. It can hash a particular piece of information. It can produce that output and it can produce a proof of computation. So you can prove to someone that you knew the pre-image of a hash without actually giving the pre-image, right? So for example, let's say password authentication, right? In traditional world, someone stores the hash of your password in their database. Now you provide your password, they hash it again, and yeah, they figure out whether you know the password or not. In this particular case, what you can do is that you can simply hash it locally on your system and provide a proof that this is the hash of whatever input I had. And if someone thinks that this is the correct hash, they know you have the password, right? So you can just combine them to create anything that you want. Now, one last thing before we actually see them in action is that not all inputs in a ZK-SNARK circuit needs to be private. So they can be private inputs and public inputs. And what we mean by public inputs is that at the time of verification, right, apart from the proof of computation and the output, the public inputs will also be required. So when I want to prove someone that I did a computation correctly, I would also have to provide all inputs that have been marked publicly. So a circuit becomes like a contract that a prover and a verifier shares between each other, where the prover says, okay, I will do this computation, and where the verifier will say, okay, you can keep these inputs private, but I will only accept I will only verify if you provide me these inputs, and you can keep the rest private. So why would we even need this? Let's take an example, right, of NFT whitelisting. So let's say you are part of NFT whitelist, and you want to prove to some verifier that you are part of an NFT whitelist. Now, the way you can do this through ZK proofs, although this is not ideally how it would be done, you will use Merkle trees, but we are simplifying it. So we're thinking that, let's say it's a list. So let's say we have a list, a simple array of these addresses, right? So your address is in it. So what you will do is that you can input your private key, although not advised, right? We are just taking an example, and then you will put all the list of public addresses, right? And what this computation can do is it can generate a public key from your private key, and then it can check that whether this public key is in any of the addresses that is part of this whitelist, right? Now, when you send this proof for verification, the only thing that this proof says is that you had a private key whose public key was part of some list, but the verifier needs to know which list it was that it was a part of. So the verifier will mark this particular list of addresses as public. So at the time of verification, you would have to provide it. And yeah, the verifier at the time of verification can then take the proof of computation, take the list of addresses, check whether it is the same whitelist as the one they have. And if it is, then they know that you are part of the NFT whitelist, right? So this is why we would need some inputs to be public. So now we will see them super quickly in action. So some biddle time. And this is where, if you're a developer, you would really enjoy it. If you're not, you can just watch it. So what is that we're going to build right now? We will build the same ZK factors application that we're talking about, an application where you can prove that you know factors of a number without actually showing them, right? So our computation will look something like this. You will have two inputs, X and Y, and you have an output Z. X and Y will be hidden inputs. And yeah, basically this is what the computation will look like. So this is what the project flow that we'll make right now will look like. We will write a ZK circuit. We talked that how circuits are how you write logic, how you express computation in ZK-SNARKs. You will compile that circuit, and then you will generate two keys. So first is a Z key, second one is a verification key. Z key is required to generate proof. So it will be required by the prover to generate its proof, and the verification key will be required by the verifier to verify these proofs. So yeah, the tech stack that we'll use right now will be SIRCOM and SNARK.js. SIRCOM and SNARK.js are developed by teams at IDEN3, and you can use SIRCOM to write these circuits. It's a programming language to write circuits, and SNARK.js is a JavaScript library that you can use to generate and verify proofs. So yeah, let's write some super quick fast code. So now to simplify application development, I made my own kind of a small framework kind of a thing, so that people can easily work with it. Just give me a second. Let me bring my, yep. Yeah, so let's just Yeah, let's just clone this repository. Again, if you're not a developer, totally fine. Like you can just watch it for next 5 minutes. Okay, yeah. So we can. Yep. Oh. So yeah, we are like cloning the repository. It is public, and you can do the same in your free time. It would be recorded, so you can see how we went through it. So yeah, let it get. Yep. So now we have it. Now we will leave this black screen because I don't want to intimidate people into thinking that we are doing something super complex. So we will now get to something that looks more better than something super black. So we'll put it. Yep. And yeah. So I hope the font size is fine because that is usually a problem when I work with. It's good, yeah.
Yeah.
Got it. Yeah, you're not watching it on a full scale monitor, right? Because in your case, then it would be. Yeah, anyway, got it. So when you enter inside this project, you see this particular template made for you. So I made it for you so that you don't have to like write all of this from scratch. So here you're declaring that you are going to use version 2.0 of SIRCOM. SIRCOM has 2 versions, and we are going to use the latest one. A template is basically like a class. So if you have worked with classes, it's like a blueprint where you're going to express what your computation is going to look like. And here you can think of component as an object, although not the exact right analogy, but yeah, you can think of it as an initialized version, right? Something concrete made out of that blueprint. So when you go and look at our circuit, which is here, yeah. So we had 2 inputs and we have to now declare them. So we come here and we say signal input X. And because like we are expressing computation in terms of circuits, we are calling the input signals and we're also calling the outputs as signal, right? So signal output Y. And then we will have a signal, signal input. Input Y. And then we will have a signal output Z, right? And anything that does not have like, for example, here X and Y will be private by default. If we want to make them public, we would have to explicitly declare that they are public, and outputs are always public. They can never be private. So we go ahead and we say Z is X into Y, right? So this is how you say it here. And then we add a hard constraint that. So now this thing will make sure, the last statement will make sure that this computation can only pass if Z indeed is equal to X into Y. So the proof of computation will now make sure that your Z was equal to the product of inputs X and Y. So now when we go, the first thing that we have to do is that we have to compile the circuit. If you look at the project flow, so again, this small framework kind of a thing I've made simplifies this for you, where you don't have to do much the way you would have to traditionally do if you deal with SNARKs or let's say SIRCOM. So you can come here and firstly I have to type yarn to install all the modules. And then you come here and say yarn compile. And interesting. Invalid syntax. Is it triple equal to? Yeah. So yeah. Now what you see is that the circuit compiled and it says that we have 1 constraint. And when we look at here, we have 2 new files, R1CS file, a .sim file. You can completely ignore it. But for now, you can think that this is the result of compilation. So let's say when you compile a C program, you get, let's say, some sort of object file. And so yeah, it is basically the result of compilation, right? And now the next step was to generate keys, right? So we need a verification key for verification. and key for a Z key for proof generation. So we come here and we say yarn gen key. Again, all of these things have been made simple by you. But if you want to take a look, I have provided all the scripts that are powering this logic under the hood inside the scripts folder. So you come here, you type yarn gen key. And yeah, here is where we look more cool. So you can look that, yeah, like a lot of random stuff will come on your terminal, but what we're trying to do is that we're trying to generate keys. The way these keys, so meanwhile, it takes some time to generate keys. So meanwhile, these keys are being generated. I want you to know is that right now, the best way to do this key generation is through a multi-party computation because there's something known as a toxic waste. And if it is not thrown away at the time of key generation, then it can result in someone faking proofs. So in multi-party computation, the way it generally happens is that a lot of people come together to generate these keys. And if even one of these people, this group was honest in removing the toxic waste, no one no one can then attack the system, right? So basically, this is how it should ideally be done through multi-party computation, where a lot of people or like nodes come together to generate, or participants come together to generate these keys. So yeah, meanwhile, we finished this definition, our keys have been generated. At the end, you will see there are two new files. This is a Z key, which we'll use for proof generation, and this is a verification key, which we will use for verifying these proofs, right? Now, the next step is to generate a proof. And to generate a proof, firstly, we have to run the computation. So we have to define the input somewhere. So you have to come and say input.json, we create a file, and we define our inputs. We say X is, let's say, 4, and let's say Y will be 3. So the output of this particular computation will be 12. And yeah, we can come here and we can say yarn gen proof. And it should take this input file and it should generate a proof. So when you come here, you see two things. You see a proof, and it is something that it's fine. It's fine. If you can't make sense of it, no one can. Like it just looks same. Every other proof looks same. And then it also generates another file known as public. So this public.json contains all public data that will be required for verification. Here it is the output of the circuit, which is 12. So if you remember, our inputs were 4 and 3. So now we have this proof of computation that this computation was done legitimately. And then we have this file, which is saying that the output was 12. So someone can verify whether, I indeed knew the factors or not. So I can come here and say yarn verify proof. I would have to firstly provide the public data, which is in my public.json. Then I have to provide my proof. I come here and it says, yeah, okay, you knew two numbers which when multiplied are 12. Let's try to change it. Let's try to say that I knew two numbers which when multiplied resulted in 10. And when I do that, and when I come here and I say, boom, it says invalid proof. Whatever you're trying to do, sir, this doesn't work. This was not what you actually had, right? So now the interesting thing is that this thing that this like small thing that I'm providing you to build your applications with, you can simply export a smart contract that can do this verification. So what I have to do is that I have to say here in the yarn gen contract, and yeah, here it is. You have a smart contract which you can now deploy on chain, and you can do this verification on chain, right? So I guess we can do that. Like, why not? Let's just do this super quickly. Let's just show this verification on like how it will happen on let's say on an Ethereum virtual machine, right? Like how you can deploy this verifier there. So yeah, but yeah, so we go to contracts, we make a new contract, we say, oh, I already have one, so I can simply delete this one and we can paste it here. Yep, so we create a new contract. You come here and you copy everything from here, paste it. And yep, so now you have to deploy it. So you come here, you firstly compile verify.sol, then you come and you deploy it on a virtual machine. Here is your contract. Wait a minute, I have to put my second screen slightly here so that I can see the first ones, this side. And yeah, here you can see here you have this thing known as verify proof. So now what you have to do is you can come here and you can generate the call data. So you can say in here yarn gen call data. And it has generated a bunch of data that you can paste into this smart contract so that it can verify the proof. So I can come here and I can put it. So the first part here, till here, it is the proof. And the second part here, this one, this is your public output, but in the hexadecimal encoding. So that is why it is C. So for example, if I come here and I paste it, right? I say verify proof. Yep, here it is. It says that cool, whatever proof you're providing is right. Let me just come here and say that instead of 12, I have, let's say 13. So I say and make it D. When I try to verify the proof on chain, it says, boom, false. That's not true. Whatever you're trying to do with me, you haven't done the compute. This proof does not prove that this was the output of the computation. So yeah, this was our small middle session that we did to just take a look on how this thing can work out. And then the next steps, if you're a developer, you should look into circumlab, circumlib, SNARKs. I abstracted the use of all of these for you through this small framework, but should definitely go and look how all of this is happening under the hood, right? And then let's just talk about a few use cases of ZK-SNARKs. The first one is scalability, although people might expect that I would have said privacy first, but yeah, scalability. And the interesting part is do computation once and for all, right? So let's look at something like Polygon ZK-EVM, right? You have transactions happening on a layer 2, right? And then you can generate proofs around how the state transition is happening from one state to another, right? And then you can submit these proofs to a layer 1, where verification can happen that whatever happened inside the layer 2, was it correct or not? There's no need to redo all of this computation on the layer 1 to verify the integrity of the layer 2, right? So basically what happens here is that you can do computations on a second layer, generate proofs of those computations, submit it on layer 1, and you get to leverage the security of the layer 1 while still do cheaper transactions on a layer 2. And the second one is privacy, which is something that I'm working in with Polygon ID. So what we are trying to make is a self-sovereign identity system powered by ZK-SNARKs. So let's say right now when you go to a particular restaurant and there's an age limit of 21. Now, when you go, you show some sort of an identity, and apart from your age, you have now made them see your residential address and a lot of other data, which was completely irrelevant, right? So the only thing that you needed to prove here was that you have a claim from your respective government, or let's say from some reputed claim issuer, that you are above the age of 21. And you should be able to generate a proof around that you indeed have this claim. And with Polygon ID, you can do something like this. So you can go to a particular restaurant, they would have a QR code. You will simply scan it and you can generate a proof that you indeed are above the age of 21. We already have all of this working. This is live. So you can test that around. I can give you, if you want sometime else, I can do a demo of this as well. But this is what we are trying to make on the privacy side. So yeah, thanks. If you really like this particular quick presentation, you can reach out to me on these particular, and yep, you can send me some feedback around this particular presentation here. So yep.
Hey, that was really amazing, Harsh. Enjoyed every bit of it.
Sure, thanks.
So I personally have a lot of clarity on what is ZK-SNARKs, a bit of ZK-EVM as well. Thank you. This was really amazing. I'll probably just head over to Matt. I'm sure he must have a lot of questions. Matt, what do you?
Yeah, Harsh, thank you so much. That was an amazing covering of how ZK works. I honestly don't think I've seen a better presentation for just getting like an entry level idea of how all this computation is done. I had a quick question for you. I was kind of curious on the ZK side. When we're talking about obviously the scalability and the privacy solutions that this technology offers, I'm sure a lot of developers were looking at this and were thinking, hey, this is super cool. I want to get involved. I want to learn more. Besides the libraries that you were showing us, is there anything that you think is very valuable for a developer who's interested in this space, who's just starting out to learn?
Yeah. So for example, these are not the only tooling available, by the way. So, but yeah, if you're getting started, I would say as a developer, you don't need to understand the hardcore math behind them, right? There are academics who are working on it and they're providing you ready to use implementations. So you have to firstly decide on which side you want to go. You want to go into the academic side of creating the schemes and providing the implementations around it, or you want to build on top of these already provided implementation, right? So but yeah, what I would say is that if you want to get on the application development side of it, just go through some very basic medium articles around what ZK-SNARKs are, what this proof actually is, and what it looks like under the hood. But you don't have to spend your time reading a lot of academic deep stuff. If you are it's not a prerequisite, of course, it always helps, but it's not that you can't start developing without reading that literature, right? So you can simply go and pick up libraries like Snark.js and everything else, and you can simply start generating proofs, right? You can start writing the ZK application. So for example, at IDEN 3, what we had was, we believed in something like Circom, a native language for writing ZK-SNARKs, but you can also go to, let's say, something like Winterfell, which is something provided by Facebook, and you can then use them to generate Stark, express computation and generate proofs around them with Starks, right? But overall, just get this. By the way, this is more than enough for someone who's experienced Ethereum developer to just get a grasp of this, that how this thing works, and they can simply start writing their own applications after this itself. So yeah, that is for the application development side. If you want to get into the hardcore part, then you need some good understanding of cryptography and set theory, groups, fields, all of that stuff. So
that makes sense. It's easy to get into, or at least easy to figure out where to start, but to really become an expert, there's a lot to grasp in this space.
Yeah, it is basically, let's say, writing applications on the internet. You simply need to know HTML, JavaScript, CSS, or let's say something like React, right? You don't need to understand how the TCP packets are. You don't need to read the RFC, TCP RFC for that, right? If you want to get into that stuff, that's a different thing. But if you want to do application development, yeah, you already have ready to use implementations.
Super interesting. And going off that point, for our audience who is focusing maybe a little bit more about how they can use zero knowledge proofs from a business perspective outside of development, why might it be valuable for somebody with not so much of a technical knowledge just to understand how zero knowledge proofs work?
Yeah, that's a very good question. So what is outside it apart from academic curiosities and the fun of making it? So for example, first of all, one example I've seen is SSI itself, self-sovereign identity, and I see huge value creation happening there. If it is powered by, let's say, zero knowledge proofs. So for example, right now, as we are going to move towards a public infrastructure like Ethereum, right? When we interact with applications, we have to make sure that our privacy is secured. And in the current system, that is not the case, right? And hence, you can do humongous value creation if you can create interesting applications of self-sovereign identity with ZK-SNARK. So for example, let's say you could go to a particular DAO and you could have a claim from Nike that you are a good runner. So let's say Nike has an app which it already has Nike Run Club. You're running and Nike gives you a claim that you are a good runner. Now, when you go to this DAO, and let's say this DAO is trying to make a DAO of all runners, right? You simply can prove that you have a claim from Nike that you're a good runner without revealing other parts of your identity. So providing tooling that can enable this can create huge value creation. So overall, privacy and scaling are two things that create huge value creation. And from someone who's looking at it from a business point of view, this is something that you can tap into. This is where you can create value. For example, like a application specific rollup or something like that, which is submitting ZK proofs to L1, getting its security at distance time, making that application on chain cheaper. So yeah, there's a lot to do. A lot of any sort of value that you can create with privacy and scaling.
Yeah, that makes a lot of sense. And I think going on that point too, we were talking a little bit about privacy, and obviously the computation that you did as a little demo, I think really like highlights like the availability of privacy. But just getting maybe a little bit deeper into that topic for you, when we're talking about these zero knowledge proofs, would you say that the information that is being protected in terms of privacy, is it like a black hole where all that information is being sucked in, never to be seen again? Or are there kind of ways for people to get around the zero knowledge proof, and it's more so like an initial shield, but if there is need be, there are ways to get through to that information?
Well, let's say, so let's look at what zero knowledge cryptography is simply doing in terms of privacy, right? So like basically what it simply does is that it is simply proving that a computation was done right. And then you can hide inputs around it. So for example, let's say, now again, it would depend what sort of a proof is generated from that computation. Let's say I generate a proof that I know two numbers which when multiplied results in 6. And it's a futile attempt because I can't hide anything in it. Although it's a proof of computation, right? Everyone will know that it's 2 or 3 or 1 or 6, right? They just have to, they know it's either the two of it, right?
Right.
But yeah, it all depends upon what the computation in itself means. Can you get around it? Well, you might know all the combination of inputs that could have made this computation pass, but then the thing would depend upon that whether you knowing all of those combination results into something or not.
That makes sense. It's very much on a proof by proof basis almost.
Yeah, it will depend upon what sort of computation you're doing, right? Like, for example, let's say I generate like a hash from a password, right? So now someone knows that a string of inputs were provided. Now they can try to brute force by executing the circuit, but like it would make no sense. Like it is like normal brute forcing. So yeah, like I would say that it really depends upon what the computation in itself is. But usually they are like they might at max what they can do is that they can leave with you an array of possibilities that this is what the knowledge could be, but you would still be equally confused what it exactly was. So in the multiplication case, you would still be equally confused whether it was 1 or 6 or whether it was 2 or 3, right?
Yeah.
And if this confusion in itself is more than enough to provide security, then great. If it is not, then that's a different scenario. You have to come up with some different way of structuring your computation.
Great. Yeah, that makes total sense. I think that's generally it for me. Mrudul, is there anything that you have to add on?
Yeah. All I know is that you're making it very hard for the kids to get into the bar because of the ZK-SNARK, zero knowledge proof and all. But definitely we have a couple of questions in the chat. So Ek wants to know if you can give us the GitHub repo for the demo, and we would love to have it, and we will share it with our team and the community. And how about how would you approach MPC redundancy in ZK-SNARK?
Which redundancy? Like I couldn't get it.
MPC.
Oh, multi-party computation. Like now that's now the thing that I say again. You have to understand that this thing is coming from like me, right? But what I think is that let's just do a multi-party computation. Let's just generate keys 1. Let's just trust that this computation was done good enough. Like let's just do a like multi-party computation with, let's say, all of these big people or whatever it is, and then let's just trust those keys. Although this might sound not the ideal way, but I think that it's fine. For example, for me, I can easily use the power of tau files like generated by Polygon for some of their big projects and simply start using it on that trust that they have done it right. But if you look at trusted setups, they need is slowly being eliminated. So in the future, you won't even need them, right? So for example, in the case of blocks, you only need to generate those keys once, and that key can be used then for any particular circuit that you want, right? So yeah, but again, I don't have a religious methodology on how it should be done. If you're using Groth, how you should approach your multi-party computation, how you should make sure that it is transparent, as much transparent as possible. Not sure on that. But I think that we are slowly moving towards a future where MPC won't even be required for key generation because we won't need trusted setups. So yeah.
Nice. Harsh, how did you get into ZK-SNARKs, Polygon? How all this happened?
Okay,
give us some background.
Okay, got it. So I was working on random ideas at that time, and one idea that came to my mind was that, so I had a friend who has a company in chain analysis, right? And he told me some pretty brilliant stuff around it, that you can just like you can just get a very interesting kind of data around Ethereum addresses, right? And I was like, wait a minute. And I was actually like surprised to see that how much, like, given we take privacy on Ethereum, although you can very easily be, indexed as a person. You can be like, someone can connect the dots and figure out who you actually are, right? So when I was looking at something like voting on Snapshot, I was like, every vote is public. People are voting from their ENS. Let's say in future, someone's Ethereum address gets exposed. Someone can create a complete profile what you look like. So at that time, I came up with my own product. It was called Votium, not the scam Votium. I later on came to know that Votium was a huge scam. So not that one, but Votium basically allowed you to do anonymous voting on chain. So basically what you could do is that you could generate a proof that you are eligible to vote on a particular motion, and then you could submit your proof and you vote. And the contract also made sure that you cannot double spend your vote, right? So I made that system around. I went to a hackathon with it. I won it. I won a track in it. And then I shared it with few people. Then it reached to someone in Polygon ID. They saw it. And then I figured out that a lot of cool stuff is happening here. So I started working here. So yeah.
Hey, that's super interesting, Harsh. By the way, I mean, there's a lot of discussion happening around ZK-EVM. Everyone's trying to be that ZK-EVM king. Scroll is in it. Polygon is there. Sync is there. I mean, can you just like give more details on why everyone is going there? What is happening?
Yeah. So first of all, ZK-EVM is a very entertaining stuff to like read on Twitter, because it's like a lot of interesting stuff happening. Like you see people comparing each other's ZK implementation and all of that stuff, and a lot of drama as well around it that people are creating on Reddit and stuff. But let's look at why ZK-EVM is a very big deal, right? So we had, let's say, something like Stackit, which came up with a solution. So Stackit, so basically, first of all, let's understand ZK rollups. I already told you what a ZK rollup is. It generates proofs of its state transition, that how it is transitioning from one state to another. It is generating those proofs, sending it to some layer one, which has great security. So you're leveraging the security of the layer one while doing cheaper transactions. So now one approach is that you create application specific rollups. So let's say Uniswap writes its own rollup, then let's say Aave writes its own rollup, right? And what happens is that this comes with huge application development cost, right? Like Uniswap would have to migrate its whole application to application specific rollup, and it comes with a lot of engineering cost, complexity, and a lot of other stuff, right? Now, what a lot of people did was that they came up with a simpler implementation, not a simple, I would call it a simpler implementation, but where they came up with their own scripting language, which is not Solidity or a EVM, or a language that can be compiled to EVM bytecode, right? For example, Stackit, right? So they came up with Cairo. You write your programs in Cairo. So you can write a text in Cairo. You can write let's say something like a flash loan thing in a Cairo, NFT in a Cairo, and then you deploy it and you use Cairo. But again, it's a huge learning curve for someone to come and learn it, although it's good implementation. But when you have a ZK-EVM, you can take any existing smart contract, simply deploy it, and just starts working, right? So it is like deploying your smart contract to a testnet, right? Like you don't have to do anything. You simply have to change the RPC, URL, and the chain ID in your deploy script, and boom, your application is now living on a very cheap but secure L2. Right. So this is why ZK-EVM is a very big deal. The reason, another thing is that it is very complex to create a ZK-EVM. And the reason is because EVM was never like at its time of creation, it was never created with the goal that it should be very easy to generate proofs of its state transition. Right. So when you look at other rollups which are not ZK-EVM compatible, they've created a virtual machine which can generate proofs as it like transitions from one state to another, right? While in the case of ZK-EVM, you have to like make it work. So if you look at Polygon ZK-EVM, it's like a lot of complex tooling that has to be created to make it up, right? So yeah, that's why it's a very big deal. It's a very complex topic. People were saying that it's going to come way huge down the line. It will take a lot of time. But it's like a very big feat that we are very near. So, yep.
Nice. That's super cool. Talking about ZK-EVMs, I would segue to EVMs because next week we'll be having Michael Kong, the CEO of Phantom, talking about the upcoming Phantom virtual machine. So just plug in here to just subscribe to our Chainstack channel and probably connect with us next week. It's around 11th, but that would be also interesting. One last question, Harsh. So I'll be asking this to everyone now, I think. What did you stack last? It can be anything. So did you stack Bitcoin, Polygon, Matic? I mean, what did you, food? What did you stack last?
What did I stack last? Okay, that's a good question. Let me think. I guess a lot of cables, like I have a lot of cables at my place, and I suddenly started finding them. So now my drawer is completely stacked with a lot of cables, HDMI cables, and a lot of other cables. Yeah, that's the nearest thing that I can see right now, which I've stacked. So yeah.
That's super cool. Hey, Harsh, thank you for coming and for the first episode of Stackit. This was amazing. We were really interested to know about ZK-SNARKs. We've heard a lot about ZK-SNARKs, and we finally did it. So thank you for joining us, and this was really amazing. Thank you. Thanks a lot.
Yeah, this was amazing for me as well. I really enjoyed it. So yep. Kudos to the whole Chainstack team. So yeah.
Thanks, Matt. Thanks for joining in as well. Sure. Matt and everyone from Chainstack is always available on our Telegram chat, Twitter, everywhere. Do check out chainstack.com. There are a lot of cool things for developers and everyone in the ecosystem, Web3 ecosystem. So do check it out. Do subscribe to our YouTube channel. And probably we'll also share personal Twitter handles of Harsh, Matt, and me as well. So that is it for today, guys. Thank you for joining in, and we'll catch you guys in the next one.